What we're going to look at now is just a different technique that we can use to graph some of these polynomial functions. What this is going to do is incorporate a little bit of the two previous videos that I did for graphing polynomials. One of them will look at the behavior at the ends. We won't need this for these first two examples, but I'll do another novel example after. And then what we can also look at is something that I did mention in the first video is what happens at the zero depending on the power of the factor that goes with that zero, and that's called the multiplicity. So if the multiplicity is odd, so for example, these won't be the examples I'm going to roughly draw on the side here, but like if we have y equals x or y equals x cubed, in those two examples, if I plug in a negative, then I get a negative, and if I plug in a positive, something on the right of the zero, what I'll end up getting is a positive. It will change signs there. So those things can look a couple of different ways. We might get something as a curve. So I'm not drawing those functions on the left, but we might have something that kind of goes through like this. So it'll cross through the x-axis at its zero. Or we might have some that actually sort of level out a little bit and then keep going down immediately after. So those are what it might look like if we have an odd multiplicity. And if we have even multiplicity, what's actually going to happen here, so we might have functions like, for example, y equals x squared, y equals x to the 4, etc. Here, both cases, we have a zero at zero, but if we plug in either a negative or a positive, we do get a positive coming out from it because it just sort of squares away the negative part to it. And so what's going to happen in these cases is instead of going through the axis, we might bounce up at the axis. And we'll see that behavior that you should have seen in the first video's graphs. So maybe something like this, where it hits the axis, but then sort of flips right back and goes down. So that's the behavior that we might get there. It'll either stay positive after hitting that zero or stay negative. So we'll start with two hopefully sort of familiar looking functions here. They're both going to be a couple of parabolas. I'll make some notes of what we know about both of these. So this is just a normal upwards parabola. And our vertex, if you recall, we can grab the vertex from the numbers. And just like with transformations, that'll be a positive 3 for x and then like a plus 0 for the y. So that vertex at 3 and 0, and I think you'll also believe me when I tell you that 3 is the 0 of this. If I plug in 3, I definitely get 0 for y. Now, as far as multiplicity, actually, why don't I label what the actual 0 is first? So the 0 of this one is at x equals 3, and the multiplicity, if you're paying attention, it's the power of the factor that goes with that root. So the multiplicity will be m equals 2. And so in particular, that's even. Now, if we use this information here to graph, if you haven't done so already, we should know that upwards parabola, it's just going to sort of graze the x-axis. I'm not going to draw any kind of scale for this. But yes, we'll have that 3 and 0, and because it opens upwards, it should look like this. And that's coinciding with what I stated before about the multiplicity, right? The even multiplicity gives us this sort of bouncing back effect here at the 0. So it hits the axis and then goes right back up. And so that's what we're seeing there. So the second one, I'm not going to graph this by putting it in vertex form because I don't like that 7 in the middle. So I'm going to graph it by just doing the zeros. So I'm going to factor it to graph. I do know that it's an upwards parabola because of the positive x squared. So I'm going to factor. It should be x minus 2, x minus 5. 5 and 2 are the two numbers that add to 7 and multiply to 10. And we need the negative to go with the negative 7. So that should give me my zeros at x equals 2 and x equals 5. And that's enough to get a pretty decent graph. Especially if I choose not to even label the y-axis because I don't really care about that scale. So I'm going to label my 2 and my 5. So my points 2 and 5. And then since it's upwards, I do know that it's got to come down and up like this, down. All right, so that's all stuff that we could have done hopefully before this class. If not, hopefully, a good enough review. And then what we're going to see here, again, we're going to look at the multiplicity. Both of these are just to the power of 1, so both of them have multiplicity 1. Both are odd, and in both cases, you'll see that the curve goes through the point. Instead of sort of bouncing back like we had on the parabola on the left. So it coincides with this notion that like odd will go through because it's going to change sign, because the negatives don't get canceled out in an odd power. In an even power, the negatives do get canceled out. So you get that sort of bouncing back effect, and it might also bounce back on the bottom. So we'll do another example. Okay, so for example 2, we've got this great big dirty looking polynomial here. It's already nicely factored, so I'm not going to put you through that. So yeah, we're going to go ahead and sketch this. I'm going to do this without the sign table. Instead, what we're going to do is look at the end behaviors and also use this sort of flipping or not flipping sign behavior that I was just describing. So yeah, first of all, we will look for that end behavior. Right, so we're going to grab the lead term. So I'm going to have an x, a 2x squared, an x, and an x cubed. X times 2x squared times x cubed. And so that will be, sorry, I put my square in the wrong place there. There we go, 2x squared like that. I guess technically, if I want to be consistent, it should look like this. Yeah, so I get x, 4, how many x's? 1, 2, 3, 4, 5, 6, 7. So I'll have 4x to the 7. And if x is going to infinity, I will get 4 times a positive infinity to the 7, which would be infinity. So y should also go to infinity. And if x goes to negative infinity, my 4, that negative infinity to the 7 will stay negative. So that's going to tell me kind of what looks like on the outside of the graph. I don't know what goes on in the inside, but I know that as x goes to the right, y goes up, and as x goes to the left, y goes down. So I know it'll look something like that. That should be a little bit to get me started. And then what I'm going to do is look at the flipping signs, as what was described above. So we're going to look for my zeros and sign changes. So we'll have 4 zeros here. X is going to give me x equals 0. 2x plus 5 will give me x equals negative 5 over 2. x plus 1 will give me x equals -1, and x minus 3 will give me x equals 3. Now on the left there, I didn't write any powers, so I am going to make sure that I include those. Only the x minus 3 also has a power, because those multiplicities are basically what dictate whether or not the sign is going to change. So here we've got multiplicity 1, multiplicity 2, multiplicity 1, and multiplicity 3. So what we're going to have is the first one is going to change. No change because of the even power. And then the other m's, the other multiplicities are odd, so the powers, so the sign will change, excuse me. And then we should be able to use that to actually put together a pretty decent graph. So I'm going to get this together. I will put some points on here. I might want to go through and actually rearrange the order, because I noticed that they're not left to right. So maybe I'll just put like little numbers beside them to tell me what order to do everything in here. -5/2 is the least most number, so that's first. And then -1 is second, 0 is next, and then m equals 3 will be the last 0. All right, so I'm going to use what's going on in the very far ends. I know that it's going to look something like this, and something like this, and the whole problem is I don't know what goes on in the middle, and that's where I'm going to use this green information here to fill in the rest of that for me. So I've got a 0 at 0, -5/2, so -2.5, and -1, and 3. And then the first one, which I'm going to label right here. So the first one says there's no change, so it's going to have to come up and back down. And the second one, all the rest of them actually do change, so I want to make sure I have that. So 2 will go through because the sign changes. 3 will go through because the sign changes. And 4 will also go through because the sign changes. And then hopefully if we've done this right, that last sign change will go up to the arrow that I've done on the right. And you can use that as a little bit of a check to make sure that you haven't missed anything. But this should be a rough idea of what this graph looks like for us. It's not great, but it should give us the same conclusion if we did it the other way. One of the reasons why I don't really like this method is because if you do make a small mistake, like if you make a mistake on the very first one, it's going to mess up all the signs after that first one, and the whole graph is just going to be way, way off. And I think it's a little bit harder to do that using the other method. So I prefer the other method. It explains why the things change a little bit more thoroughly than this method does. And it's also that technique of finding all those signs is something that we can extend it to graphs that aren't polynomials and aren't factored like this. We can do it with things that are going to have some exponentials or even trig pieces in them. And it's also something that you're going to want to be fairly good at. If you're taking calculus, you have to do all sorts of inequalities. So I don't recommend this method, but it's faster if you're good at it. So there you have it. There's your graphing polynomials.